So I'm a computer scientist. I've done research in information visualization, and this is my first time at the ALife conference. This is my way of reaching out to a new community, and I have an anecdote about ALife and myself. So about 30 years ago, when I was a teenager, I remember reading about this field called artificial life and the Santa Fe Institute, and I was really interested, but I didn't have access to the internet. So I wrote a letter on paper to the Santa Fe Institute, and I introduced myself as a high school student, and I asked, do you have any information you can point me to learn more about this artificial life thing? It sounds really interesting. And someone at the SFI actually took the time to reply. They found printed copy of the proceedings of some conference. I don't know what the conference was anymore. It may have been an early edition of ALife. And they put these proceedings, they're about an inch thick, they put them in a big envelope and sent them to me in my to my address in northern Quebec. So I'm a teenager, I received these, I'm very happy to receive them, I enjoy flipping through them. I can't really understand much of what's written in them, but here I find myself decades later. I'm a researcher and I'm attending the ALife conference, and it goes to show when you help a stranger, when you help a young person, you never know what's going to come of it. So for the talk, I'm going to show you different ways to visualize data, and I like to subdivide data into two big categories. There's what we could call tabular data, and then there's what we could call network data. So tabular data is sort of like numbers, and network data is topological type stuff. And then within the category of network data, there's a subcategory which corresponds to trees. So I'll show you different ways of visualizing all these types of data. In between tabular and network data, I'll talk about color, so ways to make better choices of color, how color is perceived. And once that's all covered, I'll make some connections with ALife. So I've chosen some papers from the ALife literature and also related literature like Origins of Life Research, and I've picked out a few figures to show you that we can critique. So I'll make some suggestions about how they could be improved, or maybe point out some things that I think work really well in certain figures. I will pitch some ideas for how to visualize the type of data that's encountered in ALife research, a few remarks about 3D, and then at the end, I'll show one more technique for visualizing tabular data, which is a technique we call the GPLOM. It's something that we developed. Okay, so tabular data. Let's look at a few examples, simple examples of tabular data, and let's think about how we could visualize these data sets. So here maybe I've got a business, and I'm looking at sales figures as a function of year. So the sales are a function of year. The sales are the dependent variable. The year is the independent variable. And I'm actually going to use the terms measure and dimension to refer to those two kinds of variables. So a measure is a function of a dimension. And we could say that this data set is a 1D, 1M data set, just to emphasize that distinction. So how would you visualize this data? How would you show it graphically? Here are a few options: the line chart, the bar chart, and the pie chart. It turns out each of these could be a reasonable choice. Each of them arguably has some advantage, and it also turns out one of them is typically recommended for this type of data. So looking at the line chart on the left, the line chart makes it easier to see small changes in slope, and that could be very useful if you're interested in data that changes over time, or data that's a function of some continuous quantity here. The line chart also suggests to the audience that it makes sense to think about interpolation, to think about interpolating between two different years, two consecutive years. And maybe that's something you want to encourage. On the other hand, maybe you want to discourage that kind of thinking. Maybe you want to imply to the audience that they shouldn't be interpolating. And so in that case, maybe a bar chart is a better choice. The pie chart makes it clearer that these different sales figures add up to some whole. They add up to 100%. And they also make it easier to make part to whole comparisons. So for example, the green pie slice here, we can see it's a little bit less than 90 degrees of the circle. So we can tell that the green sales, the sales in 2013, are a bit less than 25% of the total sales over all the years. But it's actually hard to see that in the bar chart or the line chart. The pie chart, though, Also makes it harder to judge tiny differences in angle. And I'll show an example of that in the next slide. So what is typically recommended for this type of data set is the line chart. So I put a green border around that. Okay, so I just claimed that pie charts make it hard to judge small differences in angle. Here's some evidence for that. So we have 3 data sets, each of them visualized as a pie chart and a bar chart. And in the bar charts, it should be clear that the first data set is increasing, the last one's decreasing. But in the pie charts, it's really hard to see that. I also said that line charts make it easy to see small changes in slope, and you can see that here. The same data set shown 2 different ways. Maybe you can see red dots here. These red dots correspond to the years. And maybe you can see that at that particular dot, there's a change in slope, and again here, and again here. But it's harder to see the changes in slope in the bar chart. Okay, here's another data set, very similar to the first. We have sales as a function of region. So maybe we have stores located in the north, south, east, west regions of the country. So in the earlier example I showed, this dimension was year, but now it's region. And region is an example of a categorical variable. What I mean by that is the different values of region are discrete things, and they don't have any natural ordering. We could order them alphabetically, but that's kind of arbitrary, and if we translate the names of the regions to a different language, the ordering is likely to change. So there's no intrinsic ordering to these things, and maybe that changes the way we want to show the data. So how would you show this data graphically? Let's look at the same possibilities we had earlier. Now with this data set, it really doesn't make sense to use a line chart, because the line chart suggests that it would make sense to interpolate between consecutive regions, and that's not the case. So don't use the line chart. The bar chart is typically what's recommended for this type of data. So I've distinguished between measures and dimensions. I also mentioned categorical variables. So it turns out that in addition to classifying variables as measures or dimensions, we can also classify them according to this typology. So each variable is either going to be quantitative, or ordinal, or categorical. Quantitative variables are things like real numbers, like money or time. And categorical variables would be things like the region. Or another example would be types of macronutrients, proteins, carbs, and fats. Okay, there's no natural way to order those things. They're just 3 different levels or 3 different values of this categorical variable type of macronutrient. Ordinal variables are discrete, just like categorical, but the discrete values they have do have a natural ordering. So maybe they can be ordered chronologically, like in the example of level of education or periods of Western music. Here's another example data set. Now we have 2 measures that are each a function of 1 dimension. So maybe we have a business that makes money through sales and also through rentals. How would you visualize this data set? Again, there are multiple possibilities. In the upper right here, we have a scatter plot. And the scatter plot's peculiar because it's not trying to show us the dimension. It's only showing us the sales and the rentals, the 2 measures. But it's useful because it makes it clearer if there's a correlation between those 2 measures. Here we have a stacked bar chart. And that's nice because it's showing us the total for each year. So if we wanted to do part-to-whole comparisons, it would be easier to do with this stacked bar chart. But the stacked bar chart has a disadvantage compared to these other 2 charts. If I asked you to compare rentals in 2010 and 2012, that's actually a little bit difficult because you sort of have to mentally translate this green segment to be right beside this green segment. Okay, and so if I ask you, how big are rentals in 2012 compared to 2010 as a percentage? So how much bigger are the rentals here? What you have to do mentally is compare the lengths of these 2 green segments, and that's a little bit difficult. It's a little bit easier in this type of chart, the grouped bar chart, because the green segment for 2010 and for 2012, they are with respect to a common origin. They're with respect to the same baseline. Okay, So what we say is that if you're comparing segments in this stacked bar chart, you're comparing the length channel, the visual channel of length, whereas over here you're comparing the visual channel of position, because what you're really comparing is the position of the tops of the bars, and they have a common origin, they have a common baseline. And it turns out that comparing positions is easier than comparing lengths. Okay, in the line chart here, again, the same type of comparison would involve positions, not lengths. Okay, so it turns out that there's a whole list of visual channels, and these channels have been ordered according to how effective they are, how easy they make it to make visual comparisons. And this ordering has been established through studies where people are shown, for example, people can be shown bars in different types of bar charts, and the participants are asked to judge what the difference in percentage is between two different bars, for example. And of course, there's some error in their answer. But what can be done if you ask many people many questions like this is you can calculate what the average error is in the case of position and also in the case of length. So if I ask some participants, what's the difference in length between the red and the blue here in percentage, and I ask the same question over here, what I'm going to find is that here the average error is bigger than in this case. Okay, so this allows us to say that the visual channel of position is more effective than the visual channel of length. And just once again, when I say position here, what I'm referring to in these bar charts is the position of the tops of the bars with respect to a common origin. Over here, we don't have a common origin between these two segments, so we speak of length. So as we go down this list, comparisons get more and more difficult, and the average error in someone's judgment gets bigger. So angle is a little worse, and that's a way to explain why pie charts don't make it so easy to compare different pie slices, especially if the difference in angle is small. Area is a little bit more difficult. Color value, color saturation, even more difficult. And then we get lower down on the list, we come to volume, color hue. So what I mean by color hue is different colors of the rainbow. It's very difficult to judge the quantitative difference in percentage between two different hues of color. And shape, sometimes shape is used to show some quantitative variable. Again, it makes it very difficult to judge differences. So this hierarchy can be used to justify design choices in a visualization or in a chart. As a designer, one of your goals could be to pick the most effective visual channels, to make use of the most effective visual channels to show the most important variables in the data, the variables that are of greatest interest to the audience. Okay. Now this hierarchy I've shown you, this ranking is valid if your variable is quantitative. If on the other hand your variable is ordinal or categorical, then the ranking changes. And so as an example of what's happening there, let's say color hue. So color hue, this would be a color of the rainbow. That's not such a good way to show a quantitative thing like money or temperature. But it's actually not bad for showing categorical data. So if you had like 5 different departments in a company or 5 different sports teams, you could simply choose 5 different colors from the rainbow to code those teams or departments, and that'd be a very reasonable way to identify those different categorical values. Here's another example data set. Here we have one measure, the sales, which is a function of 2 dimensions, the year and the region. So how would you visualize this data? It turns out there's many options available to us. So here I'm showing some of the more commonly used ones. We've got variations of line chart and bar chart. Here we have 2 kinds of grouped bar charts. This one's grouped by region, this one's grouped by year. So here each color corresponds to a different year, and here each color corresponds to a different region. The 3D bar chart, and some additional possibilities I've generated down here. So heat map and parallel bar charts. These are things I created in Excel using something called conditional formatting, which you can look up if you're curious. If you prefer using Google Sheets, there's a feature in Google Sheets called Sparklines, which allows you to do something similar. So let's look at each of these charts. what can we say about them? Well, the three charts that are here, the group bar charts and the overlapping line chart, they're all making use of the position visual channel. So if you wanted to compare sales for a particular year and region versus sales for another particular year and region, you would be comparing two different positions. And so you're in the best ranked visual channel within the hierarchy. So that's great. The stacked line chart and stacked bar chart, they have an advantage, which is that they show us the total for each year, the total across all regions for each year, and that might be something useful for us. They also have a disadvantage, and that is for certain comparisons, we end up having to compare lengths instead of positions. So there's a trade-off there. The 3D bar chart doesn't have either of those advantages. Some of the comparisons involve length, and at the same time, it's not showing us totals for any year. And then even worse, it suffers from occlusion. Okay, so 3D bar charts are sort of considered kitschy. You probably shouldn't be using them. Maybe the only advantage they have is that maybe in some cases they look kind of sexy, or they can be sort of eye candy. Maybe that was the case more like 1 or 2 decades ago, but there's a wider understanding that these things are generally a bad choice for showing data. So I don't recommend those. If we look at the heat map and the parallel bar charts, one advantage that they have is they don't require us to choose a color palette. We don't need to have a different color for every year or every region. So they scale better if we start adding more years or more regions. Another thing to notice is that in the variants on the right here, I've put numbers on top of the cells. So this is a way of combining two things. We're combining the visualization, or the use of some visual channel, along with text labels. And the visual part allows an audience to quickly see trends, outliers. An audience can quickly see if something is increasing or decreasing, to see where the big things are, the small things. That's what the visual part really gets us. And then the text labels on top allows the audience to read in detail precise information for a particular cell that's of interest. So anytime you can combine the visual and the textual like that, that's often a good thing to do. And we could add text labels to these bar charts. So imagine at the top of each bar we could put a little text label showing us the exact quantity, and you can imagine improving that a little bit by rotating the text labels 90 degrees so that you can make the text bigger. In fact, the entire chart could be rotated 90 degrees, and that way you could make the text labels bigger and they would also be easier to read. So these are little tricks to enhance the charts. If we look at the heat map, one disadvantage of it is the visual channel it's making use of is color, right? If I go back here to my hierarchy, we're showing sales, so that's quantitative, and we're making use of color saturation. We're making use of this thing. So we're not, it's not a visual channel that's as effective as position of length. But on the other hand, it does scale better if we have lots of years or lots of regions, because you can imagine increasing the number of cells in this heat map, eventually getting to the point where each cell occupies just a single pixel, and you would still be able to show the quantity in each pixel. So here's a summary of what I just said. Another example of a data set. This data set has more variables in it. The ones we've seen so far, all the data sets we've seen so far had 2 or 3 variables. Here's one with more, and I've chosen this example to look something like what we might encounter in a relational database. So if I'm running a music store and I sell musical instruments and sheet music, maybe every time I have a sale, there's a new row that gets added to this table. So how might we visualize this data? And actually, before thinking about that, maybe it'd be worth asking which of the columns in this data set are dimensions and which ones are measures. That might help us think about this. So it turns out that in this particular example, there are no dimensions. Everything's a measure. If there were a dimension, that dimension would allow us to uniquely identify a row, and we can't do that here. So what is sometimes done in databases is there's some column that gets added. It might be called a primary key, or you might think of it as an index, and that thing will uniquely identify each row. So that primary key or index would be the dimension, and everything else would be a measure that's a function of that primary key. So this type of data, I've been calling this tabular data. We could also call it multidimensional multivariate data. So sometimes that acronym is used, MDMV. We could also call it relational data. Now, why the term relational data? Why do we speak of relational databases? Well, because in math, there's this concept of a relation. A relation is a subset of a Cartesian product of sets. So imagine you have the set of all client names and the set of all products, the set of all prices, the set of all dates, and then imagine forming the Cartesian product of those sets. You'd end up with a big set of tuples, right? And every tuple would have as its first element some client name, as its second element, its second component, it would have a product, and so on. And what this table is doing is it is determining a subset of that big Cartesian product. It's enumerating certain tuples within the set of all possible tuples. Okay, so this table actually is a subset of a Cartesian product, and in that sense, it is a relation, and that's why we speak of relational databases, and sometimes people call this relational data. Another example, which we could interpret as relational data, would be a video. Now, this is a bit of a weird example, but imagine a video the way it's made up of a sequence of images, a sequence of frames. And then each frame is made up of pixels. Each pixel has some position and some color, RGB, red, green, blue, color components. You could enumerate all those pixels in a big table, and each pixel would correspond to one row. Okay, so it has some position, X, Y, it occurs at some time in some frame. Those are the color components. Now this is maybe a strange way to represent a video, but you could represent it this way, and then you could ask, which columns are the measures, which ones are the dimensions. So it turns out there's 3 dimensions in this case. If we specify an X, a Y, and a time, that allows us to uniquely identify a row, and then we can look up the color. So the color is a function of these first 3 columns. So there's lots of data sets that can be thought of in terms of being tabular or relational data. And as a designer, we're free to choose how we're going to map the columns in this data to things in the visual representation. So the video, we could decide that we're going to show it as a sequence of frames laid out side by side like this. We could decide to show it as a volume, and there's research that's been done in visualization of video as volumes. We could also do something strange, like let's say we want a 3D scatter plot of the color components, and then we take each pixel from the video and we plot it somewhere in this 3D scatter plot. So there's one pixel, there's another, and another. Now this might be a very strange way to visualize video, but my point is that as a designer, we're free to choose the mapping from the columns of the table to the different things that are available in the visual representation. Okay, so we could take a step back and we could think about how to define the visualization or the design of a visualization. In a sort of abstract sense, what we have on the left is a data set. And in this data set, there could be many variables. Some of them are dimensions, some of them are measures. They could be quantitative, ordinal, categorical. And what we want to do is choose some mapping that sort of projects that down to some visual representation. And the visual representation is very limited in a sense, because we're limited to working with 3 spatial dimensions at most, maybe only 2. Often we want something that's flat. And maybe we have 1 temporal dimension if we allow for animation, but maybe we don't even want any of that. So it seems like the problem here is very constrained. But fortunately, we do have many visual channels that are available, and there are also some tricks that we can use, which I'll show examples of. There are tricks to map multiple variables in the data to a single spatial axis in the visualization. So if we do have a data set that has many variables, what are some techniques to visualize such data? I'll show a few examples. We've already seen a few that hint at some techniques. So the parallel bar charts and the heat maps could be ways to visualize many things. Next, I'm going to show examples of glyphs, which are a way of showing many variables at once. And there are some other techniques I'll get to in a moment. One of the earliest examples of glyphs are these things called Chernoff faces, which were proposed as a way of visualizing statistical data. The idea is that you have a face, and the face has many parameters. It's got eyes, it's got a mouth, and you could play with the size of the eyes, how ellipsoidal the eye looks versus how circular it looks, the curvature of the mouth, does it look more like a smile or a frown, the nose, each of these parts of the face has a size, maybe an orientation, maybe a color, and all these things are different parameters that could be mapped to different variables in the data. So in this example, someone's taken different drugs and different data associated with different drugs, and they've visualized each drug as a face. So these faces are an example of a glyph, and a glyph could be many other things other than a face. Here we have arrows as glyphs. So there's a discrete grid here of positions on a geographic map, and at each discrete position there's an arrow showing the direction and the speed of the wind. So this is a way of visualizing a vector field. In this particular work, the authors, not only did they want to visualize the direction and the speed, they also wanted to visualize the uncertainty in the direction and the uncertainty in the speed. So on the left here, they played with different designs, different visual designs of glyphs to show all those things. And on the right, there's one particular glyph they've chosen to show that. So if you imagine this data set as a table, what would the columns be? Well, there'd be columns for X and Y, right, or latitude, longitude. And then there'd be columns for the speed of the wind, the direction of the wind, the uncertainty in the speed, and the uncertainty in the direction. And then you could ask, okay, of those columns, which ones are dimensions and which ones are measures? Well, in this case, the latitude and longitude would have to be the dimensions, because those allow you to look up the values of the other columns, right? The other columns are functions of latitude and longitude. Another example of a glyph, candlestick charts. Each little candlestick is a glyph. And so these can be used to show financial data, the changing price of a stock over many days in this example. So the top and bottom of the candle show the closing and opening price of a stock, right? What was the price of the stock at the start of the day and the end of the day? The color of the candle shows whether the price went up or down over the course of the day. And then the little line segments, the wicks that are above and below the candle, they show the min and max price of the stock over the course of the day. So there's many kinds of glyphs that can be used or designed. You can take an entire chart, like a little bar chart, and shrink it down. And each bar in that little glyph can be a parameter to show some variable. One more example. This is a visualization of countries. So each country is a disk. The color of the disk corresponds to the region of the world. The diameter is the population of the country. And here the life expectancy of the country is shown vertically. The GDP per capita is shown horizontally. So the countries that are more developed are up in the upper right corner. There's also a way to play an animation. So as the animation plays, we see the year shown in gray here in the background. It advances, and as the year advances, we see the disks moving as countries become more developed. So there's several variables being shown here, right? There's life expectancy, GDP, population, region. Those are all measures. And then the dimensions, in this case, there'd be two dimensions. One of them would be time, so the year that we're interested in. The other dimension would be something to identify the country, so the name of the country, for example, and that's a categorical dimension. So if it's interesting to compare some of the examples I just showed you. These are all examples that make use of glyphs, but if we look at what's going on with the axes, the one I just showed you with the countries, both of these axes are measures. And then the example with the candlestick charts, we've got a measure vertically and a dimension horizontally. The time is shown horizontally. In the case of the vector field or the wind, we've got dimensions on both of these axes. So a glyph can show many measures. It's sort of easy to add more parameters to a glyph just by making use of the color of some part of the glyph or the orientation of some other part, or you can add more little graphical things hanging off of a glyph if you need more parameters. That's sort of easy to do. But showing more dimensions is difficult. And with glyphs, we're often limited to showing at most 2 dimensions. it's difficult to show more than 2. So that's a limitation with glyphs. They're good at showing many measures, but not so good at showing many dimensions. Now there's some interesting software to consider to sort of understand some of the things that I've shown, and also to see another technique for showing many variables. Tableau is this software that can open up a CSV file or a spreadsheet, or it can connect to a database, and it has heuristics built into it to automatically figure out which columns in the data are probably dimensions and which ones are probably measures. So it shows the user the list of dimensions and measures that it found. If it makes a mistake, the user can drag and drop between these two panels to correct mistakes. And the user can also drag and drop from these things to different parts of the interface here and over here. And depending what is dropped and where it's dropped, Tableau will choose automatically some set of charts to show the user, the data that's of interest. So Tableau can support line charts, bar charts, stacked bar charts. It has a feature called Show Me to automatically switch between different ways of viewing the data. And it always makes a pretty reasonable choice about how to show the data. It can show data on top of a geographical map. Now here's one example I'd like to dig into in a little bit more detail. What's going on here is that 4 variables have been dragged from the left panel here over to the top. And you can see here we've got columns and here we've got rows. Those correspond to what's being shown over here. So in columns, there's 3 main columns here: central, east, and west. And those are related to the region variable that was dropped here by the user. So the region variable has 3 different values, and within each column there's a subcolumn for each day of the week, Sunday through Saturday. That corresponds to the weekday variable that was dropped in here by the user. In rows, we've got 3 rows. There's home office, corporate, and consumer. That's the market segment that was dropped here. And then within each row, there's a vertical axis to show us the sum of sales total. That's what was dropped here by the user. So the user simply dropped in these 4 variables, and this was automatically generated by Tableau. So here's a schematic to show more abstractly what's going on. These 4 variables get dropped in, and what Tableau does is it recursively subdivides space so it can fit more and more axes into each cell of a table of charts. And so this strategy of recursive subdivision of axes, we could call this dimensional stacking. That's one of the terms that's used in the literature. And in the example I just showed, line charts were chosen to be shown within each cell. Why line charts? Well, because the last 2 variables that were dropped in were a measure, that's what's green here, versus a dimension, that's in blue. Okay. On the other hand, if we drop in 2 measures as the last 2 variables, well, we end up with scatter plots because that's more appropriate for 2 measures. So this strategy of dimensional stacking is another way to show many variables at once. Okay, here's an exercise to make some of this more concrete for you. If you like, you can pause the video and try this exercise out for yourself. So imagine you're given a data set of models of automobiles. Now this is an example I took from an article by Jock McKinley. It's several years old. So if you're someone who knows about cars, maybe these models of cars are going to sound very old to you. But nevertheless, there's 19 models of cars in the data set that you're given. So those are like 19 rows in the table. And the table has 5 columns, one for the model of car, another for the price of the model, another for the mileage, so how efficient is the car, the repair record, how reliable is this model of car, and the weight of the car. And the exercise is to figure out a way to visualize this data. How would you go about visualizing it? Keep in mind that the 2 variables that you're most interested in showing the audience is the price and the mileage, because those are the 2 things that will have the most influence over a decision to purchase a particular model of car. Okay, so one strategy you could use to design a chart would be to go back to the hierarchy of visual channels and think about what channels could you use to show these 2 variables as effectively, as clearly as possible. And then if there are ways that you can show the other information, that's even better. But it doesn't, these other variables don't need to be shown as effectively. So you can pause the video if you like. think up some solution. At the end of my talk, I'll show some example solutions. But for now, I'll just carry on. Okay, other techniques to show many variables at once. We've already seen glyphs and dimensional stacking. So parallel coordinates are another technique I'll show, and the scatter plot matrix. I'll show examples of those. There are other techniques for doing what's called dimensional reduction. And maybe you've heard of PCA or multidimensional scaling, or if you're familiar with the machine learning literature, maybe you've heard of TSNE. So TSNE is another way of doing dimensional reduction, but I'm not going to talk about those. I'll just talk about parallel coordinates and scatterplot matrix. So to explain what those things are, consider another example data set where we have a group of students in a table. Each student is taking these 4 courses, and we have the mark that each student got in each course. So each student is a row or a tuple in this table. How could we visualize this data? Well, the parallel coordinates technique, the idea there is that each course becomes a vertical axis, and each student becomes a polygonal line that intersects each of these axes at some position. So this particular student I'm showing as the black polygonal line got 90% in physics and 95% in math and so on. A second student we could add in red got different marks. Okay, and so we could add many students, they would become many polygonal lines intersecting these axes. The scatter plot matrix, the idea there is we're going to show one scatter plot for every possible pair of variables. So the scatter plot that's here corresponds to math versus physics. This scatter plot here is French lit versus math and so on. So I've arranged this to cover every possible pairing of variables. And then each student becomes 1 point in each scatter plot. So this student in black appears in each of the scatter plots. That's just one student with these marks. A second student we can add in red, and we could continue adding more students. Here's another data set, similar data set. We got 5 students, 4 courses, 1 student's in blue, 1's in red, and you can see on the upper right there's parallel coordinates, on the upper left is a scatter plot matrix. Now the way I've shown the matrix here, it should be clear that every pair of variables is covered, because I've got all the 4 courses listed as rows and also as columns. So obviously every pair is covered, and in fact this matrix of plots is redundant. It's a symmetric matrix, right? Because let's say this plot, for example, the scatter plot, this is math versus dance. Well, that's the same thing as dance versus math. So to save space, what we could do is just remove the upper triangular half of this matrix. So that's what's being done here. And we could even remove the diagonal of the matrix, because the diagonal is not particularly informative. It's simply showing us math versus math and physics versus physics. So often the upper triangular half and the diagonal are removed, and we're just left with this. Another example data set, this time shown in a scatterplot matrix. These are different automobiles. So we've got miles per gallon, number of cylinders, displacement, horsepower. So we could look at all this data, and then at a glance, sort of, we might be interested in identifying correlations or outliers or trends. And so this is one way of showing an overview of many variables. Another example, this is a scatterplot matrix of some seashells, I believe. So we've got the sex of the seashell, the length of the shell, the diameter, the height, and so on. So notice here that the diagonal is being used to show labels to identify each of the variables. Here's the same data set, again, cars, shown 2 different ways. The matrix here is kind of interesting because the diagonal is being used to show histograms for each variable. And also the cars here are colored according to the number of cylinders in the engine. So is it 4, 6, or 8 cylinders? All right, so I've shown you a variety of techniques for visualizing tabular data. Some of the techniques can be applied to simple data sets to just show a few variables at once. And I showed you a few techniques for showing many variables at once. Right? So dimensional stacking, that's what is used in Tableau. Glyphs, parallel coordinates, scatterplot matrix. These all the techniques I showed for multiple variables share a common limitation, and that is that they don't really scale up very well to many dimensions. They can show many measures, but not many dimensions. And so there's a question being left here: how can we show many dimensions at once? And I will answer that question at the end of my talk when I show you the GPLOM technique. But for now, I'll just leave it open. So moving on to color. On most humans, the retina has 4 different types of photoreceptor cells. 3 of them are called cones, and one of them is called rods. And here we see the response curves for these different photoreceptors. So the cones are each tuned to a different frequency that they respond most strongly to. And the cones are used during daytime in normal lighting conditions. They're used to distinguish colors. The rods, there's only one frequency band that rods respond to. Rods are active at nighttime in dark vision, and they're also used in peripheral vision to sense motion. So the fact that most humans have these 3 types of cones is the reason why we have 3 primary colors when we speak of the color wheel and how to mix colors together. And if you went through an education similar to mine when you were very young, maybe you were taught that the 3 primary colors for painting are red, yellow, and blue. So red, yellow, blue, those primary colors come from a tradition in art, a tradition that's probably over 100 years old, maybe a lot older. But today we have a more sophisticated understanding of color. And when it comes to paints and pigmentations, the way they mix, we know now that a better set of primary colors to use is cyan, magenta, yellow. All right, so when you buy ink cartridges for your printer, you probably look for CMY color cartridges. And it turns out that the way light mixes on an LCD screen or other types of screens is different. The way the light mixes in that case is an additive mixing, whereas with pigments, it's a subtractive mixing. So in an additive mixing of colors, the primaries are different. They turn out to be red, green, and blue, and maybe you've heard the term RGB. So in an additive system, a mixture of 2 colors emits all the frequencies of the components. And if you mix all 3 primaries, you get white. With a subtractive system, each mixture absorbs all the frequencies of the components, and if you mix all 3 primaries, you get black. And while we're on this slide with these response curves, I'll mention something about color blindness just briefly. It turns out that the genes that code for the green and red response curves here, the genes responsible for those, it turns out that they're located on the X chromosome. And men have 1 X chromosome, women have 2. And what happens most commonly in color blindness is that there's some allele in these genes that causes the response curves to be shifted. So either the green gets shifted closer to red or vice versa, or maybe one of these photoreceptors is completely absent. And because the red and green are coded for on the X chromosome, if a man has one of these alleles, he's sort of stuck with it. He can't really do anything about it. So the allele will be expressed. But these alleles are recessive. So in a woman, if she has one of these alleles on only one of her X chromosomes, the other X chromosome acts sort of like a backup. And it won't be expressed unless she has the allele on both of those chromosomes. Now there's also another gene on a different chromosome, chromosome number 7, which codes for the blue photoreceptor. But what we usually see in color blindness is something to do with the red or the green response curves. Either one is shifted closer to the other, or one of them is absent. And the way we perceive color is each little part of the retina has some photoreceptors that are responding to the different frequencies that are present in the light that's illuminating that part of the retina. So based on the ratio of signals here, our perceptual system perceives some color. And so if these response curves get shifted closer towards each other, that's going to make it more difficult for us to distinguish reds and greens as they would appear to a person with normal vision. Okay, so color blindness actually affects men more frequently than women because they only have one in the X chromosome. It's about 8 or maybe 10% of men who are colorblind, but for women it's maybe 1% or less than 1%. So that's something to take into consideration if you're choosing colors for a visualization. If you've chosen the colors red and green, maybe maybe those aren't the best colors, or maybe you should allow the user to change the color palettes in case they're colorblind. So colors, we can think of colors as having three components, these three primary colors. And these three components sort of act like a basis for a vector space, right? If you think of the set of all possible colors as points or a vector space, the primary colors are the components are kind of like basis vectors. So red, green, blue space or RGB space is a commonly used space within which to situate colors. Another one that's really useful is HSV space, so that's hue saturation value. So imagine a cone where the central axis passes through all shades of gray. It's got black on the bottom, white on the top. Along this central axis, we have the saturation set to 0. And what's varying along the axis is what we call value, which is it's very similar to lightness or brightness. So setting saturation to 0 but value to the maximum gives us white. Setting both of them to 0 gives us black. And then as we increase saturation, we move away from the central axis and we get colors that are more and more vivid. And at the maximum saturation, we're located along the circumference of the base of this cone. And those are sort of the pure colors in the rainbow. So the base of the cone is being shown head on in the top figure here. So it turns out we have many fewer blue photoreceptors than other kinds of photoreceptors, and that makes us less sensitive to blue light. So blue text on a black background doesn't show up very well. There's a lack of contrast. And this is seen in blue text on a black background, also a blue dot on a black background. Maybe you can see this blue dot. It's hard to see, probably. It turns out that for the same reason, yellow on white is difficult to see. Because if you think about yellow, what is yellow really? It's a mixture of which primaries? It's a mixture of red and green in an additive system. And white is a mixture of red, green, and blue. So the only difference between yellow and white is in the blue components, which we're less sensitive to. So there's, again, a lack of contrast between yellow and white. So I've got 4 pieces of text here, blue on black, blue on white, yellow on black, yellow on white, and I have the 4 dots with the same colors, and you can probably see which ones are more apparent. So any pair of colors where the only difference is in the blue component, those 2 colors are going to be difficult to distinguish. So prepare your eyes to see text that's hard to read. Okay, here's examples of pairs of colors where the blue component is the only one that's different between the foreground and background. So of course you should avoid all these combinations of colors for text on some background, or for any small details like thin lines or dots. You shouldn't be using these pairs of colors. So that's one guideline we can keep in mind for choice of colors. In general, saturated colors are better for small details like thin lines and dots and text, whereas desaturated colors are better for large areas and background colors. So desaturated colors, I would also call those pastels. So these are colors that are closer to shades of gray. So that's the second guideline. Another guideline I'd propose, and has been proposed by others, is if you're choosing a color palette to encode a categorical variable, try to choose colors that have simple names, one-word names that are easy to remember. The colors that we see here on the left, in most languages, maybe all languages, they all have a single name, which makes them easier to remember. On the right, I have an example where there's multiple shades of blue and multiple shades of colors that look orange or red or yellow, and these encode different types of governments. And so because there's multiple shades of similar colors, it can be difficult to remember what's what. And so, for example, if we look at the United States, it's some shade of blue. Which one is it in the legend? Is it that or that? It's a little bit difficult to see. It's not immediately apparent, right? Or if we pick another, for example, Saudi Arabia, is that this shade of orange or that shade of orange? It takes a little bit of careful examination to figure that out. So if we can avoid that, if we can use colors that are very distinct for categorical variables, that's preferable. And I'm going to show some examples of ways that we could color code thin lines on different backgrounds, either white or black or gray. And what I'm going to propose in the examples I'll show you is that a 50% gray background might be a very good background to use to make it easier to distinguish foreground colors of thin lines. Also avoid red and green color coding because color blindness, which affects about 8% of men, very often involves a difficulty in distinguishing these colors. Or if you really want to use these two colors, maybe it's good to offer the user an alternative pair of colors. For example, people who are red-green colorblind normally have a very easy time distinguishing yellow and blue. Okay, what if you want to use a color to encode a quantitative variable? What we often see in scientific visualizations is this sort of rainbow spectrum or rainbow color palette. It's very commonly used, but this is actually not recommended by experts in visualization. If you'll recall the hierarchy of visual channels, this type of scale is making use of color hue, which is not as effective as color saturation or color value to show a quantitative number. So if we pick a single hue like green and we simply vary its value or its saturation, that's better for allowing an audience to judge and estimate the difference in value between two different shades of that color. Sometimes we want there to be some threshold or a zero value to separate positive and negative values. So in that case, what we could have is a discontinuity in the color palette like we see here. So this scale goes from black to red, fully saturated, and then there's a discontinuity taking us from blue to white. Okay, so if we go back to thinking about categorical variables, let's say we have thin lines, maybe these are curves or maybe they're connections in a network, and we want to color code them to show some categorical variable. How could we choose the foreground colors? If we only have a small number of categories, it's pretty easy. But once you get to 6 or 7 or 8 different categories, it gets more difficult to choose colors that are easy to distinguish, especially on thin lines. And so this is a problem that I've encountered in, multiple times in the past with different projects with students. And finally, I tried a more systematic approach to choosing colors. I have here 27 different combinations of foreground colors. So I've taken each of the red, green, and blue components and I've varied them systematically between 0%, 50%, and 100%. And in the background, I have 5 shades of gray from fully black to fully white. And if I just subjectively sort the foreground colors into groups that seem sort of logical to me in shades of green and shades of blue and so on, I end up with this. And then it seems to me that I'm able to squeeze a bit more information out of a 50% gray background because it seems to me that there's a slightly larger number of foreground colors that I can easily distinguish. Okay, so here's what that looks like in practice. I've got my 50% gray background. I've got some polygonal lines here. This is actually a parallel coordinates plot. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different foreground colors I've chosen. Each of them can be labeled with a single one-word name to make it easier to remember them. And it looks to me like these are easy to distinguish. And the same colors can be applied to areas or envelopes. These are sort of envelopes of subsets of tuples within a parallel coordinates plot. And I've used some alpha to make them semi-transparent, but I can still pretty much distinguish all 10 colors here. Now, if you'd like a challenge, I would ask you to try to do the same thing with a completely black background or a completely white background. Try to pick 10 foreground colors that can be applied to thin lines that are easy to distinguish. Even better if they all have one-word, simple names to make it easier to remember them. And I think you might find this difficult to do. I find it easier to do on a 50% gray background. Here are some other examples of different ways we could. So this is a quantitative variable now being shown with the color. So on the left is a rainbow spectrum commonly used in scientific visualizations, and this is not recommended. And on the right, we have the same data set, but with a different color scale. Now there's a discontinuity. And on the right, we can very easily see the shoreline around Florida. And we can see, I think this is the depth of the water and the elevation of the land. So think in terms of the hierarchy of visual channels. What studies have shown previously is that if we picked 2 points and asked a participant to estimate the difference in percentage between the 2 quantities shown by those 2 colors, their judgment here would be better than here, because here we're using the color hue, and here we're using color value or saturation. Another thing to notice in the image on the left is there are artifacts. It looks like there's something going on between the green and the blue and the green and the yellow. It looks like there are boundaries there, but maybe those boundaries are just artifacts of the color scale that's being used. So that's another reason to not use a rainbow color map. Here's more evidence of why you shouldn't use rainbow color maps for quantitative variables. So one thing about rainbows is it's not immediately obvious how yellow and green should be ordered. So it's not super obvious which one is closer to red or closer to blue. If you take a moment to think about it, it does become clear. But it's not as immediately obvious as when we have shades of gray, for example. And here in the figure 2, the same data set shown with two different color scales, color maps. And notice again, artifacts. It looks like there are boundaries between this blue and that cyan, or between the red and the yellow, between the yellow and the green. But those boundaries aren't really there. They're just an artifact of the color scale that's being used. What if you wanted to show a quantitative variable using color on thin lines? Well, on the left, we're using a rainbow color map, a rainbow color scale, with two different backgrounds, white and black. And you see, with the white background, it's hard to see the foreground colors that are closer to yellow. And with the black background, it's harder to see the foreground colors that are closer to blue. And again, this is color hue that's being used in the foreground, so we're not very well positioned in the hierarchy of visual channels. On the right, we are simply varying the saturation of the color. So we're going from white to red, white to cyan. That works well on a black background. Or in the upper right figure, we're going from black to red. So we could say that the value is what's being varied there. And it looks pretty good to me on a white background. Okay, now if you are colorblind, or if you know someone who is colorblind, you probably do, even if you don't know it, this might be of interest. So these are some filters that were accidentally discovered that block some of the frequencies located at the overlap of these response curves. And so if a colorblind person puts on these glasses, it won't allow them to see new colors that they couldn't see before, but it can sometimes allow them to more easily distinguish things like green and red. And that can be sometimes quite important. I mean, think of traffic lights, for example. So you can actually buy these things that are like sunglasses, and I think they cost somewhere between $400 and $600 US. Okay, so in the beginning of the lecture, I talked about tabular data. I showed examples of how to visualize that. Now we get to network data. So for me, this is a completely different category of data. There's different techniques for visualizing them. When I say network, I mean the same thing as a graph, as the discrete mathematician would use the word graph. So it's a set of nodes and a set of edges that connect nodes. How do we visualize these things? Well, it turns out there's a whole field of study called graph drawing, which sort of grew out of computational geometry. And graph drawing now there's multiple books about it. There's an annual conference, or maybe it's technically a symposium. I think it's called the International Symposium on Graph Drawing. And every year they publish new algorithms for computing layouts of networks. And there's also software, free software that you can get to compute these layouts. So these algorithms can produce very nice output. And if you want to program an algorithm like one of these, unfortunately, a lot of the algorithms are rather complicated. You might have to read not just one paper to understand an algorithm, but multiple other papers that are cited by it. They can be rather tricky to implement. However, it turns out there are a set of layout techniques that are much simpler to implement. So I'll show a few examples. One is this general idea of force-directed layout. So imagine that the network is a physical system. Each node is a mass. Each edge is maybe a piece of string or a spring holding the two nodes together. And we want to simulate some forces acting on the nodes and on the edges. So a simple approach could be to imagine that every pair of nodes is repelled, maybe because they all have a positive electrical charge. And in addition, every edge is a spring. So think of Hooke's law, wants the nodes to be a characteristic length associated with the spring. So if we simulate these forces and we have uh, uh, a loop that iterates, and for each iteration it computes the net force acting on each node and then moves each node a tiny bit in the direction of the net force. If we keep repeating this, maybe the layout's going to converge. One problem that arises is how do we choose the time step for such iterations? If the time step is too small, we end up wasting a lot of computation and we take a long time to converge. And if the time step is too big, maybe we won't converge. Maybe we'll suffer from instability. There's a hyperlink on the slide that takes you to this online demonstration. If I hit randomize and then turn on force-directed layout, we see that the simulation of forces causes the nodes to settle down to some positions. Now, if I'm impatient and I increase the time step, we end up with some instability. And that's because the forces being calculated sometimes are very big, and the time step is such that the nodes end up being moved very far away. So we could add a little hack in the code. We could impose a maximum displacement at each iteration, but that doesn't solve the problem. There's still these vibrations and instabilities. If, on the other hand, we set the time step to be very low and start over with some random positions, well, then we're wasting lots of computations because it takes a long time to converge. So there's this problem of how to choose the optimal time step. So there's various tricks that have been proposed to solve that problem of the choice of time step. One technique, which is not well known, and it's surprisingly easy to program and it's very, very effective, is this thing called stress majorization. So there's an article that explains it. When I tried to read this article, I found a lot of the material in maybe the first 2/3 of it a little bit intimidating. I couldn't quite understand all the details. But then there was a surprise. When I got to equation 12, the article sort of says, all this math we've just shown you, you don't really need to program all the equations we showed you. You could just program this equation number 12, which we haven't tried, but we think it'll also work. And it's a lot simpler to program. So I did try programming it, and it was surprisingly effective. This algorithm has some nice properties. It's guaranteed to converge. Now, it's not guaranteed to converge to a global optimum. It'll converge in general to some local optimum, but it's guaranteed to not suffer from any instability. You don't need to worry about choosing a time step, and it also converges a lot faster than naive force-directed layout. So if you're interested in the details, I suggest you look at equation 12 in this article. And you can also check out the notes on this slide for how to compute some of the input to the algorithm. So there's equation 12 from the article. Okay, another layout that's really simple to output is this thing called an arc diagram. The idea here is we take all the nodes in the network and we lay them out in a column or a single row along one dimension, and then the edges can be drawn as circular arcs. Maybe we draw the arcs as 180-degree arcs. We can also apply some algorithms to compute a permutation of the nodes, like here between the diagram on the left and the one in the middle. The only thing that's changed is the ordering of the nodes has changed. So in the middle, the ordering has been chosen to reduce the average length of edges, but it's the same edges in the middle and on the left. And the algorithm that was used in this case is what we could call the barycentric heuristic, or barycenter heuristic. We could take the same ordering and draw the same thing, but now instead of using 180-degree arcs, we could draw 100-degree arcs, so they take up less room horizontally. And one thing that's nice about these arc diagrams is there's all this space to the right, which can be used to show other things. So there's a perpendicular direction which can be used to show maybe time, or to show multiple versions of similar networks or the same network, and highlight differences between them. Maybe each of these nodes has some time series data associated with it, and that can be shown with something like a line chart extending to the right of each node. So this barycenter heuristic, if you're interested to know the details, there's some pseudocode given in a tutorial paper that I wrote in 2012. If you search for the word tutorial, you can find the paper. Essentially, the idea is that we want to sort of sort these nodes so that each node ends up closer to the average position of its neighbors. Okay, so for each node, we compute the average position of its neighbors, and we sort the nodes according to those average positions, and we keep repeating that. And there's one or two tricks we can use to make it converge faster and be more stable. Another technique that's been used to show networks is using an adjacency matrix. And maybe you're familiar with using an adjacency matrix to store a network in memory. It can also be used to show visually a network. And this might seem like a strange way to show the data, but adjacency matrices actually have some nice properties. So here we have the same network shown as a node link diagram and as an adjacency matrix. In a node link diagram, in general, you'll end up with some edges that are crisscrossing each other. And if you have a lot of edges, this can become a problem. You can end up with occlusion. It can be hard to see where the nodes are or read labels if there's too many edges. But in an adjacency matrix, there's no occlusion at all, right? Because every edge corresponds to one cell, or actually two cells in this matrix. It would correspond to two cells if the matrix is symmetric, which would be the case if we have an undirected graph. But if it's a directed graph, then of course the matrix is not symmetric. One problem with the adjacency matrix, though, is it's hard to see pathways that connect multiple nodes. And so what's been suggested by some researchers is to augment the matrix by adding arc diagrams along the sides of the matrix. We can show the same network in multiple ways. We can also sort the nodes, so that means sort the rows and the columns of the matrix, using, it turns out, using the barycenter heuristic or something similar to it. And the effect of that sorting is that the edges end up clustered closer to the diagonal, and that makes it easier to see structures within the network. So I've got a few examples of such structures. On the left, you have a node link diagram, and I've circled a few structures like cliques and clusters and bicliques. And here are the corresponding structures within the matrix after we've sorted the rows and columns of the matrix. So again, there's an explanation of this in this 2012 article. Here's a comparison of three different layouts of the same network. So node link, matrix plus arc diagrams, and this is a circular layout. By making these comparisons, we might notice things like how big the labels are. So for a given amount of space that we want to take up on our screen, different layouts can result in different sizes of labels. Like the labels here are significantly bigger than the ones here, even though it's the same network, the same number of nodes. Just by virtue of changing the layout, we can make the labels bigger. But it comes at the cost. In this case, there's a cost of having overlap between the edges, and that can lead to readability issues, which we don't have with the matrix in the middle. Okay, so trees, we can think of trees as a special type of network, and there's a whole bunch of ways to visualize trees. This type of diagram we might call a classical tree visualization, or sometimes it's called layered or hierarchical. This way of drawing a tree is, I think this was made popular by David Hillis, if I'm not mistaken, for showing phylogenies. So in this case, the tree extends radially from some center, some root node, and maybe it's a phylogeny showing different groups of animals that are splitting off, groups of life forms splitting off from each other. In this case, not only are there labels associated with each of the leaf nodes, but there's also some bars here, and I don't actually know what the bars show. Maybe they show number of species or some other quantity associated with each leaf node. But it's interesting to note the combination of different types of information being shown here. Another example of a tree structure, this is a recipe I got from this website, Cooking for Engineers. The idea is we have the ingredients listed on the left. The ingredients are like the leaf nodes, and then the successive operations in the recipe are shown as internal nodes. The last operation is the root of the tree. There's a survey that's been done of different ways of visualizing trees, and this survey has been published as a paper. There's also a companion website called treevis.net. This is an interactive website where you can view thumbnails of hundreds of different ways of visualizing trees. I think there's more than 300 of them now on the website. And you can filter these techniques according to whether you're more interested in 2D or 3D or explicit or implicit. There's different criteria you can give to filter the techniques. You can also search by keyword. And for any given thumbnail, you can click on it and have a reference appear so you can search for the paper that describes that technique if you're interested. One particular technique, which probably deserves to be better known, is the tree map. So the idea in the tree map is the root of the tree is shown as the outermost rectangle, and its children are inside it. So the children recursively subdivide the space inside the parent. What's nice is during this recursive subdivision, the area that's allocated to each node can be proportional to some quantity associated with that node. For example, if we're visualizing files, maybe the outermost rectangle, the root, could represent the entire hard drive, and each folder within it could represent a folder under the hard drive at the top level, and the size could show how many bytes are taken up by each folder. Or in the example on the right, I think these are different sectors of the economy or different sectors of the financial market, and the size somehow shows maybe it's the market capitalization for that sector, and then within it are individual, maybe these are companies or stocks. So again, maybe the areas here are proportional to market capitalization, and the colors might show something like, has the stock value gone up or gone down? So up for green, down for red. Those are commonly used colors in finance, red and green. But remember, a lot of colorblind people have difficulties distinguishing red and green. So the website where I've seen this visualization actually has an option to switch to a yellow-blue color encoding for people who would find that easier to distinguish. Another example of a tree map, the Philippines has many islands within it, and they're divided into 3 regions. So here we have a tree map. The Philippines is the root node. It's got 3 children under it, Mindanao, Luzon, Visayas, and each of those is subdivided into individual islands. Each rectangle has an area proportional to the geographic area of the island. Here we have a comparison of many ways of visualizing trees. All of these representations were computed to fit within a square of the same size. Okay, and this is work that we did to start to analyze the space efficiency of these different tree representations. We were interested in what happens when the tree gets deeper and deeper and there's more and more nodes. What happens asymptotically to the size of the smallest nodes and the size of labels that we might want to put on those nodes? So we did an analysis in this article of the asymptotic behavior of all these different tree representations, and that allowed us to rank the representations according to their space efficiency. And there's a video that explains that if you're curious. In the next part of the talk, I've taken a few figures from papers from the ALife literature and from related fields like origins of life. And we can critique these figures and see what things maybe work well and what things could be improved. So here's one example from a survey paper, and this figure is showing the number of papers published related to different themes over the years. And what struck me here is that it's kind of unusual to be mapping colors to years, to use a color palette for time like this. So if we take the same data, we can put this into Excel and generate charts like these. So here I think it's easier to see the evolution in the number of papers published in each theme. So now the color palette is mapped to the different themes. And we have something similar over here with the stacked bar chart. Another way we could visualize this data would be with parallel bar charts. And in that case, we don't need to choose any color palette. And within each theme, within each column of this table, we can look and see the evolving trend, the evolving number of papers each over time. Another example from a different paper. Here we have sort of a grouped bar chart, but the bars are quite thin and they have different colors that are quite distinct, and there's also black borders around the bars. So this creates a lot of sort of spatial noise. This could be redrawn in sort of this style. So I've sort of roughly redrawn each of the subsets of bars using the same colors, but just drawing the polygonal lines instead of bars. And we use a lot less ink that way. Here's an example where these are overlapping line charts. So there's a different colored curve for different populations of things. And there's a very simple problem. It's that yellow contrasts poorly with white. So that would be very easy to fix just by choosing a better contrasting color. Maybe also, as I suggested earlier, maybe changing the background color to 50% gray. Another example where we have thin lines, and the person who made this figure used pastel colors for the thin lines. So if you'll recall, one of the guidelines for the use of color is to use saturated colors on thin lines. Here's an example where desaturated colors are used on thin lines, but I think it's justifiable. So there's a network here, and the edges in the network are in gray on a white background, so they're not very contrasted, but I think it's justified here to make the text labels in the foreground legible. And I actually really like the use of color in this figure. And I suspect that the text labels here were probably manually positioned so that there'd be no overlap between the text labels. Here's an example where the background colors are probably too saturated. We could very easily get away with using pastel colors for background colors here, and it would probably look easier on the eyes. This is a nice use of pastel colors in the background to show different categories or groups of things. And notice the text, the black text, is always easy to read on all the background colors. Here's another nice example of a desaturated color in the background, the gray region here to indicate some subset of the network, and there's also a bit of red here to indicate something else. So that these are nice uses of unsaturated colors. This is a nice use of transparency, very nice use of transparency on the right. Let's see, there's three different colors here. And for each color, red, green, blue, there's an opaque color and also a semi-transparent color. So I guess there's 6 different categories of things here. And it seems to me we can distinguish all of them. So it's a very nice, attractive use of transparency. But it seems to me we're also probably at the limit of what we could expect to distinguish using transparency. If we tried to add a 4th category of things, it might get to be too much. So in that case, we could consider, rather than overlapping all the curves, we could draw them in separate side-by-side charts. This is an interesting visualization of different ways of folding synthetic proteins, or computational models of proteins. And the colors indicate number of contacts in the folded proteins. And there's 4 or 5 different colors in the caption. But at first glance, it only looks like there's 3. There's sort of a blue background color, and then a reddish color, and we can also see little bits of orange. But it's hard to see a 4th color. So what I did is I grabbed this image and then edited the colors in an image editor, and I simply changed the colors to this. And the idea I had was to use desaturated or darker colors for the colors that cover more pixels, and to reserve the more saturated, brighter colors when there's a smaller number of pixels involved. So maybe you can see more easily now that there's sort of a dark gray for the background, a lighter gray, and then within that there's yellow, and then within that there's little dots of red. You can certainly see dots of red here, and maybe you can also see them here. This sort of agrees with the guideline that says use desaturated colors for larger areas and saturated colors for small details. This is from a paper that showed figures of different cellular automata. And I presume that in these cellular automata, the authors don't know ahead of time which colors will end up covering more pixels and which will end up covering few pixels. So maybe the colors here are sort of random. But we could imagine adding a little algorithm that would count how many pixels are covered in each color and would automatically change the colors to be more pastel if a larger number of pixels is involved. So imagine the background colors here, instead of being saturated red and green, they could be something very pastel. And the colors that are on a smaller number of pixels, those could be chosen to be saturated. Here's a visualization of the tree of life, and this is quite nicely done because along the circumference here, I presume what's going on is the angle or the arc covered by each taxon or each subtree is proportional to the number of species. So this allows us to see where there's more variety of life forms. And you can also see radially there are these dashed ellipsoids that give us an indication of time. So we get some idea of when there were different speciation events. So this is very nicely done. Here's another visualization of something similar, another tree of life. And this is a sort of a more rectangular coordinate arrangement. So all the labels now are oriented the same way, and they're oriented horizontally, so it's easy to read them. We could also easily imagine this diagram being put inside a window and allowing the user to scroll up and down, and maybe even zoom in and out to make the text bigger or smaller. And so by scrolling, that gives a very natural, familiar way to navigate. And I actually counted the number of labels in this diagram. There's 95 labels, which is interesting because in this diagram, there's almost the exact same number of labels. So this type of radial tree layout for phylogenies, I think, was made popular by David Hillis and maybe his colleagues. So in this diagram, there's 96 labels, and if we compare it to the previous one, 95, it's almost the same number of labels. Okay. Now, thinking very approximately, we might say these two diagrams cover roughly the same area. Let's say, just for the sake of simplicity, that the area covered on the screen is 1 by 1 foot. Okay, it doesn't really matter what the units are. But if you'll agree with me that this is covering approximately 1 by 1 foot, and there's roughly 100 labels, that means the height of each label is about 1/100th of a foot. Over here, if you'll agree with me that this also covers roughly 1 by 1 foot, the diameter of the circle here is very roughly 1 foot. The circumference is roughly 3 feet, right? Pi times 1 foot. So if this is a 3-foot circumference circle, and there's roughly 100 labels around it, that means the height of each label is about 3/100ths of a foot, so 3 times bigger than here. Okay, so these are very approximate numbers I'm throwing around, but I want to point out that by thinking in this way, we can understand why certain layouts allow the text labels to be bigger than others. And that could be one criterion we use to choose one layout over another to make the text labels bigger or more legible. This is another visualization of the tree of life, which has, I think, gained some attraction, some popularity. It looks quite aesthetically pleasing. It looks very organic. However, I wonder if there was some way to adjust it to eliminate some of the white space that we see here and maybe here as well, to make it a little bit more like this. Because if we did that, if we could spread out the labels and the leaf nodes a little bit more and fill up some of this white space, we might be able to make the labels bigger, right? And maybe one difficulty in this case is it's difficult to figure out where exactly the root should be, but there might be ways to deal with that and still end up with a layout that's more like this. These are various 3D bar charts or 3D plots, surface plots I found in different papers. Almost all of them are difficult to read, except maybe this one, but it's sort of an accident that we can see almost all the bars here because there's so little occlusion. But in general, I would recommend avoiding these types of 3D views in a static PDF. So how else could we visualize this data? Well, if you think in terms of measures and dimensions, in all these cases, I think there's one measure and there's 2 dimensions. So we have 2D, 1M data. How do you visualize that? Well, I showed a few different ways to do it. One way would be to use a heat map, or another way would be parallel bar charts, and there's other options which I showed earlier in the slides. So of course these don't suffer from occlusion. Okay, this is a more interesting example, I think. This is a type of network called a RAF, and RAF, let's see, did I write it down on the slide? A RAF is a reflexively autocatalytic and food-generated set. So it's a type of autocatalytic set. There's 2 types of nodes in this network. The black nodes are molecules or reactants, and the white nodes are reactions. So the edges here are showing which reactants participate in which reactions, and the dashed edges, the dashed arrows, show catalysis. They show one molecule catalyzing some other reaction. And then the bit strings here are just labels to identify the different molecules. So I wondered to myself, how could we modify this diagram to make it easier to read? So for example, the nodes I find are quite small. It's rather difficult to tell the white from the black ones unless we look closely or if we zoom in. So an obvious change to make would be to make the nodes bigger, to make the distinction between white and black easier to see. But I wondered if there are ways we could play with the layout of the nodes. And it turns out that within one of these RAF sets, there are sometimes sub-RAF sets. So there's subgraphs which also form these reflexively odd catalytic and food-generated sets. And this is one example from a paper. So each subgraph is identified with this sort of bubble or envelope. But when I was looking at this, I was trying to confirm and convince myself that these were in fact RAF sets or RAF subsets. And I found it quite difficult to think about them and to confirm that. And I wondered how we could modify the layout to make it easier to think about them. So I very quickly and roughly redrew the same network in PowerPoint, not taking too much care in the choice of colors. But what we can see here is I've given two different colors to the nodes according to the type of node. So reactants are in gray, reactions are in orange. These are not necessarily the best colors to choose, but it's just something I chose quickly. And then for the edges, if we go back, you'll see there's two types of edges, right? There's the edges that show participation in a reaction and dashed arrows that show catalysis. So I wanted two types of edges, and I used that with the black and the blue edges. And actually, in the original figure, the catalysis edges are shown with curved edges, and that's a very nice thing to do because it means that if you have two nodes which have both kinds of edges between them, they have both an edge in black here saying this molecule participates in this reaction, and as well the dashed arrow saying this molecule catalyzes the same reaction. When you have both of those edges, the fact that one of them is curved ensures that the two edges can be distinguished visually. You don't have one edge on top of the other. Okay, so that's a very nice thing to do graphically. But when I redrew it, I didn't have an easy way to make those curved edges. So I just chose sort of a lazy hack. I made the blue edges thick and in the background. So when the two kinds of edges, black and blue, are on top of each other, you can still see both of them. But that's just a hack. It would probably be nicer to draw these blue edges as curved arcs. Anyways, now that we've redrawn the network this way, we could play with different layouts. So I thought it might be interesting to draw the network more explicitly as a bipartite network with all the reaction nodes on one side and all the reactant nodes on the other side. And then we can play with reordering these nodes to try to reduce the edge length and make reactants closer to their corresponding reactions. I also played with drawing envelopes around the subgraphs of interest. So this is one of the subgraphs, one of the subrafs. This is another one. Here's three more. And if we show all five of those at once, we get this with some transparency. So this gets a little bit difficult to read, but in defense of what I did, there's also a lot of overlap here. And so when we show the network this way, maybe it can be easier to look at a reaction, look at the reactants that are involved in it, and check visually if this subset is indeed a complete RAF set. Okay, so there's a few more examples in the slides, but in the interest of time, I'm just going to skip over them. Now, here are some ideas for applying visualization to artificial life research, which I'm going to pitch. So one of them, let's say you have a simulation of an artificial chemistry, and you're interested in visualizing the evolution of different molecules that are showing up in your chemistry, and maybe in particular you're interested in the appearance of increasingly complex molecules. So you could imagine a chart where one axis is time, And maybe you're showing line charts of the population of different molecules. So maybe they're simply overlapping line charts. But we could show even more information if we think in terms of glyphs. Maybe each molecule could be shown as a glyph. And so what I've sketched here is 5 red glyphs. Each one corresponds to a different kind of molecule. And maybe the horizontal position of the glyph corresponds to when the molecule first appeared. The vertical position could be something else. It could be maybe some measure of the complexity of the molecule, maybe the number of atoms or some other measure of complexity. And then the glyph itself could show us additional measures. So in this case, I've imagined that each glyph could be itself a little shrunken down line chart, maybe showing us the population or concentration of each molecule. So, and you can imagine fitting lots of these on the chart using transparency, or maybe even shrinking these things down. How far could we shrink them? Well, one idea comes from some previous work in visualizing time series data. So in this work, there were dozens or even hundreds of time series that the designers wanted to visualize. And they allowed these to collapse time series down into a single row of pixels. And in that case, they used color to show the measure of the time series. But if you'll recall the hierarchy of visual channels, color isn't the greatest way. It's not the most effective way to show a quantity. So the user can also optionally expand any of the time series into a little line chart. And in that case, the vertical position of the curve shows that same measure. So the measure is being shown redundantly in 2 ways here, with the color and also with its vertical position. And for the ones that are expanded, well, they take up more space, but they're a more effective way of showing the value. For the ones that are collapsed, they take up less space. So this same sort of idea could be applied to these kinds of glyphs, where you could allow the user to collapse them down into a single row of pixels if you wanted more room to show more such glyphs. Another idea, maybe you're simulating an artificial chemistry or some other simulation, and maybe you have some mechanism in place to branch off different versions of the simulation with different values of parameters. And maybe this is automatic, or maybe it's controlled by the user, some type of steering. If you'd like to visualize all the different branches of a simulation, there's prior work that you could look at for ideas. This is some work called World Lines. And so you could take a look at the paper there and look at the different ways that they've incorporated visualizations into a sort of timeline visualization. If you're interested in cellular automata, imagine a 2-dimensional cellular automaton. You could imagine it as sort of a bitmap that evolves over time. That's kind of like a video. And there are researchers who have done work visualizing video sequences as volumes. So for example, in this work, here we have footage of a hallway taken by a security camera, and we're interested in any activity in the hallway at nighttime, for example. So if a thief comes into the hallway, they're going to change the pixels for several frames. And what's being shown here is sort of this volume of the video shown as a semicircle, and some filtering has been applied to only show the pixels that are interesting, where there's some movement. So maybe something like this could be applied to cellular automata to visualize the cellular automaton changing over time. There's also ideas that might be interesting in volume visualization for medical images. So this is an image that looks like of someone's brain, and some clever filtering has been applied to make certain things inside the brain more visible, like tumors or other structures. And so we could imagine taking ideas from work like this and applying it to cellular automata, maybe to make certain events or processes apparent. For example, maybe you're really interested in walkers in Conway's Game of Life. So you could invent a filter that would make those things be more visible within a volume. Another idea for visualizing volumes, this is work on visualizing dynamic graphs or dynamic networks. So a network can be visualized as an adjacency matrix. If the contents of that matrix is changing over time, we can imagine it as a volume. And I have a video to show you that shows some of the features of this particular piece of work. So I'll play you some excerpts of this video.
We switch to an alternative color encoding, coloring cells according to their position in time from blue to orange. Cubics provides several predefined views on the cube. This small cubelet widget can be used to navigate between them. If we click on the right face, the matrix cube gets rotated so that we obtain a picture of the network's topology in the time projection view.
So I'll fast forward to another part of the video.
General temporal evolution of the network. We rotate the cube to the vertex projection view and clearly see a trend towards more collaborations, except in 2008. We now want to compare time slices and see why 2008 was different. We switch back to the time projection view and can browse through all time slices by hovering these labels. While this can work nicely for small networks and when comparing individual time slices, having all time slices at a glance allows us to quickly spot 3 phases in the evolution of this network: an initial growing phase, a restructuring phase, and a relatively stable phase in the end. Similar to time slices, we lay out all vertex slices and can compare individual activity patterns.
So this sort of very flexible rearrangement of components of a volume might be something interesting to think about if you're interested in visualizing volumes of cellular automata. And also notice that in the video I just showed you, when the user changes to a different point of view, there's a smoothly animated transition between the views. And they take some work to program, but they make it very easy for an audience to understand what's going on as the user switches from one view to another. Okay, so a few comments about 3D visualization and virtual reality, augmented reality. These are sort of hot topics in the past few years. Various companies have come up with VR headsets. VR headsets now are, of course, available for many video games on Steam. I think there's hundreds, maybe over 1,000 video games for VR available on Steam now. And there's also companies like Microsoft coming out with the HoloLens and HoloLens 2 for augmented reality. So these open up new ways to interact with the space around us. And it's exciting to think about ways that they could be used to visualize data. Maybe I can say a few words about the HoloLens 2. So the HoloLens 2 has what's called inside-out tracking. So you don't need any external devices for the HoloLens 2 to know where it is in space. And it can track fingers on your hands. It also has a built-in eye tracker for one eye. So it allows you to see the physical world around you, and it can show virtual 3D geometry floating in space in front of you or around you. And virtual reality headsets are more mature in the sense that they cover a wider field of view. So headsets like the HTC Vive or the Oculus, the latest Oculus headsets, they cover almost the entire field of view of the human eye. So in that sense, they're quite mature. With augmented reality headsets, one limitation that we still have is they don't cover as much of the field of view. So for the HoloLens 2, for example, horizontally covers about 44 degrees of field of view, which is not bad. It's not perfect, but it's enough to show interesting, useful information to the user. Now the question comes up: is it useful? Is it interesting to think about using these headsets to visualize abstract information like trees or networks or cellular automata evolving over time? And so the answer, it really depends on the type of data that you have. If you have data sets that have sort of a natural embedding in space, so for example, a medical image of someone's brain or a 3D model of a building or a car, this is data that we could say is naturally 3D or intrinsically 3D. And in that case, there is value in showing it to a user in 3D. And if you show it to the user using a headset, so they see it stereoscopically, and when they move their head, they can look at it from different points of view, that's going to allow them to understand the data set more easily and more quickly. Okay. But on the other hand, if you have some abstract data set like a network or a tree, you're probably better off visualizing that in 2D. And there are several studies that have given convincing results of this, that usually it's a bad idea to show abstract data in 3D. Usually you're creating more problems and you're better off just showing the data in 2D. So there's several reasons for that. 3D is more complicated to understand. There's occlusion. It's more complicated to interact with, to navigate within 3D. And it's also, of course, more complicated to program visualizations that are in 3D. It's more difficult to share them with other people. If you visualize abstract data using 2D, you can make use of a technique called multiple coordinated views, which is very powerful. So this is the idea of having multiple two-dimensional viewports of the same data and allowing the user to do things like point at some part of the data in one viewport and having the corresponding elements in the other viewport highlight. So you have this sort of coordinated simultaneous highlighting whenever the user hovers over something or selects something. This is very powerful, and it comes with no extra occlusion. So it's usually a better idea to try to do something like this in 2D to understand complicated data rather than start showing something abstract in 3D. Now, if you do decide that you want to use a VR or AR headset to visualize some data, if you're visualizing abstract data, I would encourage you to consider visualizing the abstract data in 2D views that are surrounding the user. So one advantage of using a headset is there's a greater space available within which to display things. And so just small head motions or eye motions can be enough for the user to switch between different virtual windows that are surrounding the user. And also in my own experience, it's a lot easier to program for VR than AR because VR is just more mature and the tools work better. Okay, so I'd like to come back to the topic of tabular data and talk about one more technique for visualizing tabular data. This is a technique called the GPLOM, which we developed a few years ago. Maybe you'll remember that one of the limitations with many of the techniques I showed for tabular data is that they don't scale well to many dimensions. So the GPLOM is a technique that addresses that. All right, so maybe you'll recall I showed this summary slide and we've got some techniques up here that I showed you for visualizing several variables at once, but none of them really allow you to see many dimensions at once. So the GPLOM is something that we can put down here to address the situation where we have many dimensions we want to visualize. Okay, so to explain the GPLOM, let's consider another example data set. We have a table with 3 dimensions and 3 measures. So this table contains data about nuts and bolts that are being manufactured by our business, by some factories that we have. And the factories are located in 3 different regions of the country. And I've called the regions 0, 1, and 2. We have data over the 12 months of the year, so I've numbered the months 0 through 11. The 2 bolts, nuts and the 2 products, nuts and bolts, are numbered 0 and 1. And for each region, for each month, for each product, we have sales numbers, equipment costs, and labor costs. And we'd like some way to visualize this data. So what happens if we use some of the techniques which I showed earlier? Let's try using a scatter plot matrix. If we use that to visualize this data, we do end up with a scatter plot of every pair of variables. And indeed, down here we have things that look like scatter plots, and we might notice certain clusters and outliers. But up here, there's something strange going on. What's going on up here? What we have up here is the variables that are being shown are dimension versus dimension, like month versus region or product versus month. Those are dimensions being crossed in the scatter plot. And so what we end up with is a grid of points simply showing us that every combination of month and region is present, or every combination of product and month is present. Okay, so that's not especially useful to visualize. So the scatter plot matrix doesn't really work well to show dimensions versus dimensions, but it works fine to show measures versus measures, like equipment cost versus sales. That's measure versus measure. That's fine, right? Or over here we have measure versus dimension. That also works all right. But dimensions versus dimensions doesn't work well on this BLOM. Another technique we might try is the parallel coordinates plot. And over here we have measures, and we can indeed see clusters and outliers. But over on the side where we have dimensions on the left, what we see again is that all combinations of these dimensions, these 3 dimensions, are present. And again, that's not very useful to us to visualize. We might try dimensional stacking, which is another technique I showed earlier. So we have 6 variables in our data set. What I'm showing here are 2 examples of combinations of 4 variables taken from those 6. So we have products, and then sales, region, and month. So those are just 4 of the 6 variables. Here's another set of 4 of the 6: products, equipment, cost, region, and sales. So we do end up with sensible visualizations, but we're not showing all the variables yet. If we add the 2 remaining variables to either of these visualizations, they end up taking a lot more space. For example, in the one on the right, we're not showing month. If we add month as a 5th variable, we end up multiplying by a factor of 12 the amount of space we need. And on the next slide here, I'm showing another subset of 4 variables. So this is, again, only 4 of the 6, where we have region, sales, month, and product. And this is already taking up a lot of space. Okay, so even without showing all 6 variables, these visualizations can get quite big. And in general, this dimensional stacking doesn't scale well to a large number of dimensions, because every dimension you add multiplies the amount of space required. Glyphs is another technique we might try, but as I explained earlier, glyphs are good for showing many measures, but they're not really good for showing many dimensions. And if you'll recall the 3 examples I showed earlier, in this example we only had 2 dimensions, and it's not really clear how we can add a 3rd dimension unless we start using 3D space, but that's going to introduce a lot of occlusion. Okay, so what's the idea of the GPLOM? The GPLOM, which is the technique that we developed, simply takes the idea of the SPLOM, and then it says within each cell of the matrix, instead of showing a scatter plot, we're going to show some chart which is chosen based on the kind of variables that correspond to that cell. So for example, down here in the matrix, we have measure crossed with a measure. So a scatter plot is an appropriate kind of chart to use in that type of cell, right? In these cells, we have measures crossed with dimensions, and there a bar chart makes sense. So we aggregate the data into bar charts. And up in the top here, we have dimensions versus dimensions. In that case, a heat map would be a reasonable choice of chart. Okay, so this is the idea of the GPLOM, and it turns out we didn't invent this idea. We thought we had, but it turns out there was some previous work. I think it's called generalized plot matrix. So that work also essentially proposes a matrix of charts, different types of charts, where the type of chart depends on the nature of the variables being crossed within each cell. But anyways, we implemented the first interactive version of this visualization, and we also published the first evaluation of this kind of visualization with users. And in the evaluation, we compared this to Tableau, and we found that for certain tasks, this kind of visualization allows the user to answer questions faster than Tableau. Because in this type of visualization, sometimes, depending on the type of question the user might have, the user can simply scan all these charts, and they might notice the chart that gives them the answer they want. Whereas in Tableau, they have to drag and drop variables to cause an initial visualization to be generated. So here's another GPLOM visualizing a whole bunch of flight delays. I think this is millions of flight delays for different reasons. And in this software, the user can select different categories within a categorical variable. So for example, the departure time block here is one categorical variable, and the user has selected something within it. The user can also select or hover over other categories and see corresponding parts of the other charts highlight. So this is work that was done by Jean-François Im, who was previously my master's student. And maybe this visualization is a bit complicated because there's 3 different types of charts, and it's got this weird triangular shape. So maybe we could simplify it by simply showing this subset of the visualization. So this is the subset where we have measures crossed with dimensions. And what this is it's a set of bar charts. In fact, we could call this a bar chart matrix. It's a matrix of all the different bar charts that we get by crossing each measure with each dimension. And this can serve as an overview of any tabular data. So it could be a way to show an overview of a relational database. So there I've updated the summary. I've added the GPLOM down here. And now, much earlier in the talk, I proposed an exercise for you to do if you wanted to pause the video. So here are some solutions to that exercise. I'll just I'll remind you what the exercise was about. If I go back here, we had a data set of 19 models of cars, and I asked you to design a way to visualize this table of 19 models of cars with 5 different columns. And remember that the 2 most important variables for the audience was car price and car mileage. So whenever I give this exercise to students, usually there's some fraction of students who come up with the solution on the left or something very similar to it. So the idea here is we have a scatter plot of glyphs where the 2 axes here are the 2 variables that I said were the most important ones, the price and the mileage. And then the glyphs, each glyph represents 1 model of car, and the glyph is chosen to show the remaining 3 variables in the data set. So in this case, the color shows the repair record, the size of the disc shows the weight of the car, and this isn't actually showing us the name of each model of car, but that could be added. We can imagine having a little text label beside each car showing us the name of the model. Another way to show this data would be to use bar charts for 4 of the 5 variables. And so maybe the advantage of bar charts here is we're making use of the position visual channel for all of the measures, which is nice. Whereas in the visualization on the left, we could say that it makes it easier to understand overall what there is in the data. We can see there's a trend, for example. There seems to be a trade-off between price and mileage, and maybe we can notice more easily if there are outliers or something like that. There are also many other solutions that are possible to visualize this data, but the one on the left is one that I've noticed many students come up with independently. So, thanks for your attention.